Hello. Today we will discuss about some of the numerical problems related to diffraction of light. So let's start. So first problem, light wave of wavelength 500 nanometer passes through a slit of 0.2 millimeter wide. The diffraction pattern is formed on a screen 60 centimeter. Now you have to determine the angular spread of central maxima and distance between the central maxima and second maxima. So you have the screen and you have a slit, and the slit gap is 0.2. So this gap D is equal to 0.2 millimeter. And the gap between the slit and screen is given as D. This is 60 centimeter. Okay, so this is, I'm representing it by capital D. And the wavelength of light is 500 nanometer. Okay, so you have to find it for the central maxima. Angular width. So the formula we're going to use here is equal to d sin theta. This is equal to some m log. So here d sin theta. So d is the slit width, sin theta is equal to m. So the angular width, one can find angular width theta from this expression. This is simply given as sine inverse lambda by d, and m, as we are talking about central maxima, so we need to find the angular width. So this is the central maxima somewhere here. So you need to think about this and this particular. So from this point, the maximas are the secondary maximas are. So we need to consider this particular angle. So this theta will be calculated for the central maxima, the angular spread of central maxima. The second one is the distance between the central maxima and second minimum. So what is central maxima and second minimum? One can think about this is the secondary maxima, and you can think about that this is the second, this is the first minima, and you have the second. So the formula what we're going to use for the two different cases. One is for the beta 1 for the central maxima and beta 2. This will be beta. So this is beta 2. So beta 2 is that for the second. So what is beta? Beta is the width of the fringe. Width of the fringe we are talking about, and the relation is given by beta is equal to d lambda by small d. D is the distance between the source and screen. Lambda is the wavelength, incident wavelength, and d is the slit width. Now see, here we are finding beta 1, where lambda d by small d. We can put the values for n equal to 1 is order 1, m equal to 1 or order 1 is 1.5. And the second one is for m equal to 2, that's for secondary one. So you can put d sin theta, and you can m equal to 2 lambda. So beta 2 can be calculated as a 2 lambda d divided by small d. Actually this formula will be modified as beta will be given as m capital D lambda divided by small. So the difference between these two, it gives you the distance between the central maxima and second minima. So we are talking about this particular distance. Okay. So you are calculating beta 1, beta 2, and the difference between these two, it gives you this particular distance. Problem number 2. The monochromatic light of wavelength 500 nanometer strikes on grating and produces fourth order bright line at an angle 30 degrees. So find the number of slits per second. So first you have to think about a grating. So grating means n number of slits are there. We need to find the number of slits per centimeter. So you have a grating, and in front of this you have a screen. So the problem is given for the fourth order, and the angle is given as 30 degrees. So m is equal to 4, theta is equal to 30 degrees. Okay. So the formula one can use for the grating, the diffraction maxima for a grating is b plus d sin theta equal to m lambda, where b we are considering the gap between the slit, and the obstacle between two slits was considered as d. So b plus d sin theta is equal to m. Now b plus d Let's take a different color. So one can write b plus d. This is equal to 1 by n. So n is the number of slits. Okay, and b and d are the slit parameters. One is the slit gap, and this is the gap between the two slits. Okay, so if you have two slits, consecutive slits are there. So this gap will be considered as d, and the gap between the slits, so this particular distance will be represented at d. So this relation is known as the Grating element relation. So now b plus d is equal to 1 by n. So now in this relation, what we are doing? We are just dividing this m lambda by b plus d. So b plus d is 1 by n. So this can be represented n m lambda. So n is the number of grating, m is the order, and lambda is the width. Now see, these are given. Angle theta is known to us. M is given. This is as 4, and you need to find what is the n. So the rewriting the formula. So this comes sine n is equal to sine theta divided by m. Put the values. Sine theta we know, and m is 4. Okay, put the values and you can get the number of lines per second. Come to the third problem. The diffraction grating of width of 2 cm, grating width of 2 cm contain 1000 lines per centimeter. So I have a slit, a grating, at the distance of 2 centimeter, this is 2 centimeter, and per centimeter we have 1000 lines. So we have total 2000 lines. Now incident light is 600 nanometer. So we need to find what is the smallest wavelength difference this grating can resolve in the second. So on the diffraction grating, when it kept in front of this light source, the light falls here. It's divided into different diffraction pattern of different order. So here this will be m equal to 0, the central one, m equal to 1, m equal to 2. You can get, so this is order 2, this is order 1. So you need to think about the order 2 where you have two different wavelengths. So you have one wavelength here, you have another. Okay, so now we need to resolve this, we need to separate them. Okay, so just refer the formula for this thing. So for the resolving power, the relation is lambda divided by d lambda. So here we are considering there are two wavelengths. So one wavelength is given as lambda, and the higher wavelength is represented as lambda plus d lambda. If you are able to resolve them, so then the difference between these two is d lambda. So resolving power is given as lambda by d lambda. Okay, this is equal to n into p, where capital N is the number of grating lines or grating slits, and p is the order. Okay. So what you have to find, the first wavelength, one wavelength is given. Okay, lambda is given in this formula, but you need to find what is lambda plus d lambda. To find lambda plus d lambda, one need to calculate what is d lambda. So rewriting this particular relation, lambda by d lambda equal to n into p. So just rewriting this one can write d lambda is equal to lambda by n into p. So lambda is 600 nanometer, and the lines are given the 2000 lines, and the order is 2. So rearranging this one can get d lambda. Okay, so you just add this one, you will get the total wavelength, the second wavelength. Now come the fourth one. The fourth one, the similar type of problem. Here, what we have to do, we have to calculate the maximum order number which will be visible with a diffraction grating of 500 lines per millimeter using the wavelength of 600 nanometer. So wavelength is given, and what is given? The diffraction grating in the order that this lines are given, slit lines. So we need to find the maximum order. So the formula for this thing is, it can be written as b plus d sine theta. This is equal to, say, some m lambda. So we need to find the condition when m becomes maximum. So for experimental setup, b plus d, which is equal to 1 by n, the grating element is constant. lambda, we are using one particular wavelength, so lambda is also constant. Okay, so to find a maximum, one need to consider the sine angle max. So sine angle will be maximum when sine theta value is equal to 1. Okay, so one can take sine, it can make a maximum value of 1. So when sine theta is 1, okay, when theta is 90 degree, so you have the maximum possible for this condition. So m will be maximum when sine theta is equal to 1. So now put this values in this equation. So rewriting this equation, one can consider sine is 1 in this expression, sine is 1. What we have done, we have taken this lambda over there, so this is divided by lambda. So a max we are kept. So sine value is maximum, this is 1. So you need to find b plus d divided by lambda. So rearranging this one can calculate. So here it comes that order maxima becomes 3.33. So here the maximum number is 3. And even you will get the part of this. So 33% after third order. So one can get 33% of the fourth order. Come to the fifth one, the fifth problem. Now in this problem, we are considering a double slit experiment. So to deduce the missing order, we try to find the missing order of double slit Fraunhofer diffraction pattern if the slit width is 0.1 millimeter and they are 0.8 millimeter. So you can just think about D is given as 0.16 mm, where B is given as 0.8 mm. Okay, we have two slits. So these gaps are D, so this is given at 0.6, and the gap between the slits is B, which is given as 0.8 mm. So what you have to find? You have to find which one order is missing. So in double slit case, we have the condition for interference maxima and diffraction mean. So interference maxima, B plus D sine theta is equal to P lambda, and the minima is given as D sine theta is equal to M. Now missing order will observe when these two angles are equal. This is given as if these two angles are equal. If they are equal, now we are dividing this expression. So B plus D divided by D, this is equal to P by M. Now put these values, D value and the B value. So it comes that the ratio P by M, the maxima and minima order is equal to 6. So if M values are 1, 2, 3, then the P is given as 6, 12, 18, etc. So one can just conclude from this, the 6, 12, 8 orders of interference maxima will be missing in the diffraction pattern. So when you have a double slit, so this order will be missing on this. Now comes the last problem, diffraction grating, which has 400 lines per centimeter, 4,000 lines per centimeter is used in the normal instrument. So calculate the dispersive part of the grating with hard order spectra, the wavelength of 4 or 5,000. So wavelength is given, the grating lines are also given, and order is also mentioned. So what you have to find? You have to find what is the dispersive power. So remember, the dispersive power formula is d theta d lambda. This is equal to m n divided by cos theta. Where m is the order, n is the number of lines in grating, and cos theta. Theta is the angle of diffraction. So we just calculate this one. So b plus d is 1 by n, the grating element. So 1 by 4,000, it gives this much. Okay. So sine theta. So rearranging this one, sine theta can be calculated from this thing. So you know the formula, b plus e sine theta. This is equal to m lambda. Okay. So sine theta can be given as m lambda divided by b plus d. And b plus d is equal to 1 by n. So just rearranging the thing. So rearranging this particular part, one can get sine theta is equal to 0.6. So when you have sine theta 0.6, one can easily calculate what is cos theta. So you need, in this formula, okay, you have to put the value of cos theta. So you need to find from sine theta, you need to find what is cos theta. So sine theta is known, you can get cos theta. We know sine square theta plus cos square theta is equal to 1. So cos can be written as under root 1 minus sine square theta. So put this value, it comes. You can get the point. Now put it back in this. So m is known, the order is known. In this case, this is given as 3. N is given, number of grating lines is also given, and theta value we have already calculated, cos theta we have already calculated. Put this back, you will get the dispersion.